Thank you very much, and thank you for having me, and thank you for being here. And yeah, I try to keep it as compact as possible in 20 minutes, and then we have time for a little discussion. And yeah, I focus today on sustainable mobility as resource regulation from an engineering psychology perspective. And Felix already said all you need to know. Perhaps one addition, so my origins, so to say, as a scientist was in my PhD on user interaction with the range of electric vehicles. So in very past times, I had the privilege to be involved in one of these first international EV field trials in Berlin and other cities, where we had also the chance to publish some first psychological research papers on EV topics such as range stress or charging user types or the range preferences of actual EV users. And psychological range, and also we did some theorizing on the structure of resource-related action regulation of EV users in everyday usage, and I will come back to this a bit in this talk today. As we are two guests today from Lübeck, also a bit more of an introduction to how is Lübeck and why it could be interesting to come to Lübeck at some point in time, maybe for HFES Europe next year, or also please feel invited, is that we are at our Institute of Interactive and Multimedia Systems. We are 5 young professors, and we are somehow covering the full spectrum of human technology interaction research based on our research infrastructure, and also with the creative young students of media informatics in a study program that focus on human-centered design, integrating design, computer science, and psychology. And this is also what my research group is about. So we work at this intersection of computer science, design, and psychology, and pursue, in the end, you could say, 3 key lines of research with focus on sustainable digital resource utilization. So in the end, we say that we as humans must balance 2 classes of resources. So our internal resources, mental and physical, and our external resources that we use. We try to understand these dynamics more precisely by going into very diverse applied contexts, such as car sharing, green shipping, so on the green line, external resources, or human basic needs and fitness tracking on the red line. And of course, we also work on all these research tools that you typically need. So like our sim lab driving simulator, our field lab for bidirectional charging, or also quite some stuff we do in scale development. For example, our ATI scale, so to assess affinity for technology interaction, that's already in use in quite some projects. Today, I focus a bit more on 8 projects that are more in the frame of sustainable mobility, but I'll come to that later because I want to give you one more perspective, which is, so from which perspective do we view, or do I view these topics that I present today? Because in each and every applied project, we ask ourselves the same 2 key questions, which are on one side, what are the key challenges for human resource regulation in this digital environment? And second, how can humans optimally be supported in their resource regulation via system design? And of course, you can get a more detailed insight when visiting Google Scholar, but you can also just take your time, practice some more German, because unfortunately some videos or more videos are in German, and have a look at our YouTube channel, Engineering Psychology, where you will see that in the core it's always about this formula being sustainability is a product of human and technology. So for example, you can see there things on energy efficiency metrics and indicators for electric vehicles, or our project Climate Crafting, which is about carbon footprint tracking, also in the field of mobility. And so this just as an invitation. And now, after like 5 minutes introduction, we go to the thing that we really want to know about, which is sustainable mobility as resource regulation. And I want to start by making more clear what I mean with resource regulation. And I would say, as a first takeaway, resource regulation is an everyday action. So you could even say every moment of our life can be viewed as resource regulation. So if you think about what are precious resources for you, maybe time. I mean, just now, like in the lunch seminar, food, maybe, good food. Maybe friends, health, mobility. I mean, every technical tool can be a resource for us. In the end, we have very, very diverse resources that we utilize, but all these resources follow the same psychological principles. In the very core, we try to achieve resource gains and avoid resource losses. And in many everyday environments, this is a continuous process of resource regulation, which is also important. So they become into play as engineering psychologists, where we are not completely rational, and it's sometimes needed that we guide users or humans. For example, and these resources also, we transact resources with one another, right? So, for example, we decide for a faster connection and exchange money for time gains, or we opt for a greener solution and accept some flexibility losses, or we say, okay, I want to arrive at Copenhagen with my electric car today, and it should have a certain charge when I arrive, so I drive as fast as is okay with regard to the energy consumption. Yeah, and so in the end, I would say that resource regulation is action regulation, and that's nice because it's a combination of cognition and motivation, and so there's quite some psychology going on. And if we want to go one step further and ask ourselves, okay, how can we structure such self-regulation or action regulation dynamics, then this feedback control loop can be quite a good guidance. And I mean, it's also inherent or a key design principle in many psychological theories and can be applied, for example, to the topic of range interaction, so user range interaction in electric vehicles, so leading in the end to the decision when to charge at home or also en route. Or it can also be used to structure this dynamic adaptation of driving behavior when one integrates different driving goals, or one wants to integrate energy efficiency in the set of driving goals that we have as drivers. But later a bit more about this. So my first takeaway for today is we should view sustainable mobility through a lens of resource regulation. Now, and if you look at the two key questions that I stated before, then applied or a bit more focused would be how can we make optimal resource regulation as easy as possible for humans? And in the end, this is a guiding question also for all these 8 projects that I will shortly point to in the following slides. And I start with one of my favorite questions, and that's what's the most efficient way to drive to my favorite beach at the Baltic Sea. Of course, the most efficient way is to use the bicycle. And if I ask what's the most efficient way to go the 40 kilometers to the beach, then if I can't use the bicycle, then the next best answer is to take the 30 kilometers route. And here's interesting to see that our most common metric of energy efficiency is energy per distance, which has no incentive for taking shorter routes. So it doesn't make us aware, so there's a certain blind spot this metric provides us. And now if I took the 30 kilometers route, then again the question is how can I drive as efficient as possible? Of course, then we have rolling resistance and aerodynamic resistance. And when it comes to aerodynamic resistance, already interesting to see that the faster you drive, the less you gain in terms of time gains, but the more you lose in terms of energy efficiency losses. So it's not a good ratio in the end, and actually I don't know who of you has a interface in his or her car to help to trade this energy consumption versus travel time metric. And of course, there's even more. Then we go into engineering. We drive, or we more and more drive with electric motors. These have a certain conversion efficiency map, and you can use this conversion efficiency map to choose the optimal speed. So, message so far. Message so far. Choose your speed wisely. But we all know that reality is more complex. Like if you think you are a bus driver, or you are in last mile delivery logistics, or you're a taxi service driver, then of course it's not just about choosing the correct speed. It's about combining all these driver goals. So of course we want to get there alive, in time, stress-free, with reasonable energy costs, and without disturbing other traffic. And we do that by adapting our driver behavior to match and balance these different driving goals. And if you have enough time, and we don't have it now, we could structure this from the control theoretic perspective. But for now, I would just point to one box in this framework and ask the question, what do safety, time, energy, and pleasure have in common? Of course, they're all resources. And here we are again with this general statement: we strive to achieve gains and avoid losses, but we have bounded rationality and heuristics and biases that also apply to driving and to energy management or resource management in the end. And we can view every control of the energy flow in your vehicle as an economic transaction of an input resource, for example, electric energy, to an output resource, which is, for example, distance driven. And each of these resource transactions can be framed differently. So it can be represented as either gain or loss. And in the end, that's the task of energy interface design, to frame these resource transactions accurately. So, for example, today when we were on the highway here to Copenhagen, which was a salient information source that informed us about the driving maneuver efficiency, of course, it was the instantaneous consumption indicator that's available in most cars. But we have found, for example, in past research, that people have something we call a peak bias. So if you accelerate, people over-representate the peak height and not so much the integral over an acceleration maneuver. And also, one has to say that this energy per distance metric is not the most accurate framing for an acceleration, because acceleration efficiency is more like how many kilometers per, so how many speed or kinetic energy you gain per invested unit of electric energy. And you can depict that, and to cut it short, you can make an interface out of it, and this can look quite nice, and it is something that is not available in any car. Maybe you would also not want it because of distraction issues, but anyway, it could be quite useful for education topics. And we examine such interfaces in our Amori project, in our electric vehicle driving simulator, which is quite, over the last 5 years, has been developed into quite a good digital twin of a Renault Zoe electric car. For example, here, that's a current study that we did, my PhD student Markus Goetker did, examining 3 or 2 displays versus no display, and how these contribute to eco-driving performance, but also energy dynamics awareness. So my key takeaway here: we need action-integrated energy interfaces, so efficiency metrics and indicators we don't have so far in electric vehicles. Now, as you know, electric vehicle driving is not just about efficient usage, but also about efficient replenishment of resources. And this is what our field lab Renobil is all about, which is a field lab for studying bidirectional charging, so green charging and smart charging with Nissan Leaf electric vehicles. We are also in the process of developing a digital representation, or you could say something like a digital twin or shadow. But André will talk more about this in his talk. And we use this lab also to do some applied research in user interface design, for example, in our project eco-share, where we design different enablers of eco-carsharing, both for individual settings, so Imagine you have a solar panel on your roof and you want to efficiently utilize your own solar power for charging, or also for car sharing. So imagine you want to book a car sharing vehicle, but the car sharing service provider wants you to optimize your booking to use or utilize green charging, also utilize the vehicle as a buffer battery. So the key question that arises here, aside from these very applied topics, is how can we make it as easy as possible for humans to behave optimally through maybe a user-centered design of AI charging agents. So not just an interface like we saw now, but more an agent that communicates, that interacts, and in the end feels like cooperating with you, and maybe feels like cooperating with you and many other users to integrate needs of different users into an optimization function. And this is something we are about to research in our project Co-Charge with Honda Research over 3 years. So maybe at some point in the future, when we enter our electric car sharing car or our own privately used car, maybe it says something like, okay, based on your data from the last 3 months, you need a maximum of 100 kilometer range tomorrow morning at 8 a.m. Are you fine when I optimize the charging to that? But of course, this project is not just about designing, but it's more about examining and a better understanding of this cooperation. And what we are here focusing is to better understand how people perceive cooperation with such an agent that optimizes certain resource utilizations in the environment. And we also have 2 talks at HCII conference during the next days here in Copenhagen. So my takeaway here is a comprehensive understanding of human AI cooperation can help us to design better smart charging agents. So and this leaves me 2 minutes for 2 last key questions. And the first one is, how do we fill, and because we can't go just with privately owned cars, so how do we fill the gap between public transport, which obviously has its limits, and private cars with attractive services? And one answer, as we all might know, is of course ride pooling, and we examine this in our projects into Lübeck, where we focus on a perspective of basic human needs versus the perception of such mobility service. And over the last 1.5 years, we have developed the perceived mobility need satisfaction scale, which is available in German and English so far, and used it in a total of 600 participants in different studies. And this is here just one example where we focused on the issue of perceived autonomy. So, of course, if you say, I use the public transport, your autonomy may be quite okay, right? So you see there's as well in the some data here on the greenish side and some data on the reddish side. If you look on the private car, of course, that's much better. I mean, you can't go much better if the parking situation doesn't limit you than private cars. And if you look in the ride pooling service that we have in Lübeck, then it's not worse, and it can even be better than a private car, especially when it comes to alcohol. Okay, so my message here is we should look at human basic needs satisfaction as a metric for good public transportation. But still there's one elephant left in the room, and that's this picture, namely all these 5,000 chips worldwide that produce 3% of our total carbon emissions, and that are about to reduce these carbon emissions by 70% until 2050, and that's a really huge task, which of course needs a lot of tech innovation, but it also needs a lot of human factors innovation, because again, there also energy efficiency is a product of technical potential and human behavior. And this is what we focus on in our project Meridata with a lot of other partners. And here we examine and investigate and design a decision support system for energy management on board. So far focused on route planning. In the future, maybe also focused on more applications that consume energy. There's also already a paper published on energy research and social science And there's some data available from our hierarchical task analysis and research on need satisfaction and automation. And these are my 21 minutes, leaving me with one takeaway. Decision support systems can support efficient energy management on ships. And this is my thank you slide.